Welcome to the second lecture of Angular Momentum Algebra. In this series, I have been discussing about Angular Momentum Algebra of an electron. And in the first series, I have discussed about the certain commutation relation that the different components of orbital angular momentum of an electron follows. If you have not seen my first video, I have given the link in the description box. Kindly do visit it. Okay, in this last video, what we discussed was the following. We took the case of an electron which revolves around a nucleus, positive nucleus. An electron is revolving around it, and its angular momentum we represented by the vector L, and in the operator form we represented by L hat. And different components of L are Lx hat, Ly hat, and Lz hat. And we derived in the last class the following relation, that the commutator between Lx and the Ly hat was IH cross Lz hat, and the commutator of Ly hat Lz hat was equal to IH cross Lx hat, and Lz hat Lx hat is equal to IH cross Ly hat. And in addition to this, we also derived the following results, that L square with Lx commutes, and similarly L square with Ly commute, and similarly L square with Lz compute. Okay, that's we derived in the last class. Well, so far we have been talking about only the orbital angular momentum of the electron, but this is not the only momentum that electron possesses. Electron has a spin angular momentum also, which is due to the spin motion of the electron. That is, the charge of the electron is also revolving over its own axis with certain angular speed. That gives rise to a spin angular momentum, which is generally represented by S. So it turns out that the spin angular momentum also follows exactly the same algebra. That is, if we measure the different component of a spin angular momentum in various directions and try to find out the commutation relation with them, it is exactly the same that the orbital angular momentum follows. It means the method that we adopted to derive these relations that we have just wrote down for orbital angular momentum. If we remember, how did we actually reach to these conclusions? We started with the definition L equal to R cross P, and then took different component of this and followed the algebra, and we obtained this relation. But spin of the electron is not something which can be written by this formula or any formula of this kind, but still it follows the same algebra. That means this method that we adopted to reach these conclusions, that it implies that these conclusions are more general. They are independent of the method that we have taken. So now, having understood that the spin also follows the same algebra as the orbital angular momentum, so we can actually write down the similar relation in replacing L by S. And since we know the total angular momentum of an electron will be the vector sum of this, which we represent by J, let's say L plus S, and in the operator form it will be like this. So since L follows the same algebra, S follows the same algebra, so J also follows the same algebra. So we can actually rewrite this whole relations in terms of J. So Jx, Jy is equal to IH cross Jz, Jy, Jz is equal to IH cross Jx, Jz, Jx is equal to IH cross Jy. And similarly J square commuting with Jx, Jy, and Jz. Okay, I have just written down the same relations that we derived in case of orbital angular momentum in terms of general angular momentum. So J is called total angular momentum or the general angular momentum, where J could be L, S, or the combination of both. We also notice that J cross J, if we try to find out in terms of operator form, J cross J, this is not 0. This is actually, in fact, IH cross J hat. How can we derive that? This is very simple. If we take the x component of the left hand side, of the left hand side, what we see, this becomes jy jz minus jz jy, which is nothing but commutator of jy jz, which is nothing but ih cross jx. These are our operators. Okay, if I skip this hat sign anywhere, it's understood that they are operator. ih cross ji. Similarly, if I take the y component, when I take the y component, I get the result as ih cross jy hat. Similarly, for the z component, I get the result ih cross jz hat. So for left hand side, if I write down, this becomes ih cross common and vector sum of 3 component, which is nothing but is cross j vector. So this relation holds. Ij cross is equal to is cross. Similarly, for L cross L, is cross L hat, and for S cross S is is cross S hat. Now, having understood all these things, let's go further and try to find out certain other interesting relations and define certain other quantities, and then we will later on find out the eigenstates and eigenvalues of different operators that we have been talking about so far. So let me define two operators further by j plus, which is jx hat plus iota jy hat, and j minus hat, which is jx hat minus iota jy hat. So from this relation, this is called raising operator, this is called lowering operator. The reason for this will be clear in a short while. Raising operator, this is called lowering operator. Reason will be clear in the due course of discussion, as I just told. So if I solve further from these two definitions, I can deduce that jx hat is equal to half of j plus plus j minus, and j y hat is for 2 iota j plus minus j minus. Okay. Now immediately it comes to our mind that we have defined these two operators like this. What will be the commutation relation of these j plus and j minus with ideas other operators like jx, jy, j plus, j minus, and j square with j plus, j minus, and so forth. Let's try to see that what is the commutation relation, for example, between j plus and j minus first of all. So what is the commutator of j plus j minus? So if I write down the definition, jx hat plus iota jy hat, comma jx hat minus iota jy hat. So I've just written the jx, the definition of j plus and j minus here, and let's try to see what this commutator is. Jx with jx commute, and for this I will have a minus of I hat, jx hat, comma jy hat, and plus I hat, I, jy hat and jx hat, and with this it will commute. So if I write down that jx and jy hat commutator is ih cross j hat, which is h cross j hat, jz hat, because this is minus iota sitting here. Similarly, for jy jx it will be minus iota h cross, which will be plus ah cross jz, this is h cross. So ultimately I obtain 2h cross j hat. So this is the commutation relation between j plus and j minus. Similarly, if I try to see what is the commutation relation with j square with j plus, for example. So this will also, if I see, this will give me jx square plus jy square plus jz square times jx plus iota jy. Okay, now jx square will compute with jx and jx square will compute with jy also, because both are in different directions. Similarly, jy square will compute with jx also and will compute with jy also. Similarly, jz square will compute with jx and jy, so this will ultimately be 0. Similarly, I can check that even for the minus case, when I have a minus here, the same story, I will get the value of this commutator again 0. Now the last one that we have to check out is relation between jz and j plus. Let's see what it gives. Jz equal to j plus is jx plus iota jy, and which is commutator of jz and jx will give me ih cross jy, while the commutator with jz with jy will give me minus of iota h cross jx, which means minus and iota square is again minus, so this gives me h cross jx plus I at h cross jy, which means h cross common j plus. So the commutator of jz with j plus is h cross j plus. While if we check the commutator of jz with j minus, this is jx, jz and jx minus iota jy, which means iota h cross, commutator of jz with jx is iota h cross jy, and minus iota commutator of jz jy is minus iota h cross jx. So minus minus plus and then iota square again minus. So we'll take j h cross minus common, to jx minus iota jy, which is nothing but minus h cross j minus. So this is the result, which we can write in this fashion, that the result is plus minus h cross j plus minus. Okay, so now let's have a look on the eigenstates and eigenvalues of these angular momentum operators j square and jz, and the action of j plus and j minus on these eigenstates. So to do that, so let's take that state like PQ. So it's a quantum state in the cat notation, PQ, where PQ are R2 index, which represent, with the help of this PQ, we represent this quantum state, P, which we are claiming that these are eigenstates of j square and jz both. Why they both will have the same eigenstates, or at least a common set of eigenstates? Because we can say because we see from the relation that j square commutes with jz. In fact, j square commute with any other component of angular momentum jx dy. So we can take any of this combination, whether j square with jz, j square with jx, or j square with jy. So nothing about special about z direction, but for conventionally we take z component. So this computation relation here represent, or they actually signify that the j square has common set of eigenstate with jz. Similarly, j square has some common eigenstate with jx, and j square will have some common eigenstate with jy. So we are taking that these common eigenstates of j square and jz is pq. So that now we define the action of j square and jz on this state. So let's say I define the action of j square on pq, or something of this kind, h cross square p pq, with j is a angular momentum which has the dimension of h cross. So if I've defined the action of j square and pq in such a fashion that h square cross square p, that means p is unitless here. P becomes dimensionless, unitless. This is just a number here. Similarly, if I define the action of jz on pq, something of this kind, so again j has a dimension of h cross, so q is again unitless or dimensionless. Okay, now once we have defined the action of j square and jz, now let's try to see that what is the action of j plus on this state. So for that we'll use a technique to find out what is the action on j plus on this. Suppose I want to find out the action of these two operators on this state, but the problem is that I don't know how j plus acts on pq, but we know the commutation relation between jz and j plus, which was jz was j plus h cross plus j plus. We had just derived this relation. So using this commutation relation, I can write down jz j plus as h cross j plus plus j plus jz acting on pq. Now we know the action of jz on pq. So first term will give me h cross j plus acting on pq. The second term would give me j plus, and jz acting on pq means qh cross and pq back. So if I take h cross common, so it is like 1 plus q j plus acting on pq, which is left hand side is jz j plus pq. So now if we look carefully, this relation, this equation tells us a very important thing. Suppose I consider this thing as a separate eigenstate, which is nothing but an operator acting on a state which will result in another eigenstate in general and some number. So this is a separate eigenstate, and Jz is acting on this and resulting in the same eigenstate and certain value here. So this is like an eigenvalue equation for Jz operator. It means this state is again eigenstate of Jz. And from this relation, we can conclude one more thing, that what is the action of J plus on this. Now, since it is an eigenstate of Jz and it is giving me the eigenvalue q plus 1 h cross, it means this state here should be proportional to something of this kind. Only then Jz acting on this can give me q plus 1, because the action of Jz is on q, on this state results me in q, not in p. Similarly, J square acting on this gives me p, not q. So this can be concluded from this relation that the action of J plus on PQ raises q by 1. That's why it is called raising operator. It raises the q index by 1. And similarly, if we try to actually see Jz with J minus and PQ, we will obtain something of this kind, h cross 1 minus q Jz acting on PQ by the same method, So again, the action of J minus on PQ is lowering q by 1. So that's why J minus is called a lowering operator. It lowers down the index q by 1. Alright. Now, having understood the action of J, something about the action of J plus and J minus in the state PQ, let's try to see one more interesting thing. What's the action of J square J plus acting on PQ? So now these two operators commute with each other. So I can write down J plus J square acting on PQ, that is P h cross square and J plus acting on PQ. Okay, so now we see again with the same logic that this becomes an eigenstate for J square, because it's returning me some value times the same state back. And the action of J plus is now, this particular equation tells me one more important thing in addition to the first one that we have seen, that the action of J plus on this state is like raising q by 1, and action of J minus on this state is like lowering q by 1. Now similarly, this important relation tells us that action of J plus on any state, because if this is a state, this is a state and J square is acting on it, it is returning me P h cross square, the similar kind of eigenvalues that the PQ state PQ state gives me. So this state should be proportional to something of this kind. P and Q may be something else, which we have seen, just it is q plus 1. Okay, so this means the action of J plus on PQ is on Q raising by 1, and it doesn't alter P at all, does not affect P at all. Okay, so with all this information we can conclude in 2 lines. So what we have seen just now is that the action of J plus on PQ is something of this kind, some constant times P. It does not affect P, it raises q by 1. Similarly, when we see the action of J minus on PQ with the same discussion, we will find some constant time, it does not affect P again, and it lowers down q by 1. Now what are these coefficients C plus and C minus that we will find in the due course of discussion little later. Now before that, let us try to find out, is there any relation between P and Q, the index P and index Q. So for that, we know that J square minus Jz square, which is equal to Jx square plus Jy square, is a positive operator, positive. If we take the magnitude, it's a positive number, because the sum of the square of two numbers, two real numbers, jx and jy. Since they are Hermitian, so their eigenvalues will be real. So this operators will always be greater than or equal to 0. So if I operate, for example, this operator in this fashion, so I'm going to get a number which is greater than or equal to 0, because these states P and Q, these are the eigenstates of J square and Jz, and J square and Jz are Hermitian in nature, so they are orthonormal eigenstates. We have taken them to be orthonormal. They will be surely orthogonal because they are eigenstates of two Hermitian operators. We have taken to be the orthonormal, that is condition of orthonormality being satisfied here in this fashion, delta P P prime, delta Q Q prime. So with this will be always greater than or equal to 0, which in turn can be written as action of J square in PQ is PH cross square minus action of Jz square on this is Q square H cross square greater than or equal to 0, which means H cross square common, P minus Q square is greater than or equal to 0, which means Q square is always less than or equal to P, or P is greater than or equal to Q square. It means Q has an upper bound. It implies Q has an upper bound. Means there exists a Q maximum above which Q is not possible, because Q square is always less than or equal to P, because Q square is always less than or equal to P. Okay, so Q maximum value Q is dependent on P. There is a relation between P and Q now that we can see from this discussion. Now the natural question arises, is there any minimum value of Q also? Because if we have found out there is a maximum value of Q, but is there any minimum value of Q also? Okay, so we'll see that in a moment, but we certainly know by now that there is a maximum value of Q. So it means there could be a state corresponding to the maximum value of Q, which is like that P Q max. Since it's a maximum value of Q max, so if I apply, for example, J plus on it, which will try to enhance Q by 1, try to raise Q by 1, but so since it's a maximum value, if it is indeed a maximum value, it should give me 0. So if I operate J minus from the left on this equation, so I will get the following. Now J minus J plus is Jx minus iota Jy, Jx plus iota Jy, P max equal to 0. So which will give me, if I open this bracket, this will give me Jx square minus iota Jy Jx plus iota Jx Jy and minus plus Jy square. Okay, Jx with Jx square plus iota Jx Jy minus iota Jy Jx and minus plus Jy square acting on P max equal to 0. P max acting on P max equal to 0. Okay, from here to here. Now if you see, Jx square plus Jy square is again J square minus Jz square, and if I take minus iota common, so this is Jx Jy minus Jy Jx, which is commutator of Jx Jy, which is IH cross Jz, and acting on P max, this should give me 0. So now if I see J square acting on this will give me P H cross square, Jz acting on this will give me Q max square H cross square, and this will iota will make it minus H cross, and Jz acting on this will give me again Q max H cross, which is equivalent to this. Now if I conclude from this equation, I get Q max plus 1. This is one thing that we have to remember. Now again, as I said in the beginning, that there is a natural question that whether there exists any kind of Q min. So let's try to find out that. We know that the action of J minus on PQ is that it reduces Q by 1. It is something like this thing. But what if I assume that there exists a let's assume that there exists a minimum value of q as q min. So if I operate j minus on this kind of state, this should give me 0. This should give me 0 because q cannot be further lowered down. Now if I operate j plus from the left on this equation, what this gives me, j plus j minus is jx plus iota jy, j minus is jx minus iota jy, and pq min is equal to 0, which is equivalent to jx square plus iota jy jx minus iota jx jy plus jy square p min equal to 0. This is p min. Okay, so this is again j square minus jz square, and this is minus iota common this time, and this will make it iota h cross jz acting on pq min equal to 0. So again this will give me p h cross square minus q min square h cross square plus h cross square q min equal to 0, which means p equal to q min into q min minus 1. This is another ratio that we have seen. Okay, let's see that the p was equal to q max into q max plus 1, and we have just derived that the p is equal to q min times q min minus 1. If we equate these two, we can derive, we can lead to the conclusion that the q max is actually equal to minus of, or q min is actually equal to minus of q max. By just equating these two relation, we can obtain this. Okay, so it means what? That suppose if q max is 4, the q min is actually minus 4. All right, so let's suppose that we can, since the action of j plus and j minus is the increase, they increase the q value by 1 or decrease the q value by 1 in integer stack. So it means the q min actually can be obtained by q max, let's suppose in n steps. So the q max is equal to q min plus n, or q min is equal to q max minus n, and we have just seen that q max is minus of q min. So if I write down here this using this relation, if I write down this equation, this will become that the q max is actually equal to n by 2, because if I replace q min by q max, so this will become 2 q max equal to n and q max equal to n by 2, and q min will be naturally equal to minus of n by 2. So that's what we have drawn the conclusions as. Now if we remember, we saw that the q was q max into q max plus 1, and q max we have just seen that is n by 2. If q min is equal to q max minus n, that is we can reach to the q min by reducing q max by 1 in n steps. So this will be n by 2 plus 1. We have just seen that the q max comes out to be n by 2, and this becomes this, and q max is so q min is again minus n by 2, and q max is n by 2. So q max is n by 2 and q min is minus n by 2. So instead of writing this, in place of writing this n by 2, let's use another symbol. Let me use n by 2 as j symbol, so that p becomes j into j plus 1, and q max will become in this case plus j, and q min will become in this case minus j. So that is the allowed values of q. Allowed values of q would be minus j2 plus j. It means 2j plus 1 values, including 0 if j is an integer. So we can go to minus j to plus j, like minus 3 to plus 3 if j is 3, so minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So there will be 7 values including 0. Alright, so in this new notation, let's try to see what is the action of our j square and j. First of all, in this new notation, how does this our states look like? So earlier it was pq, so now p is j into j plus 1 and q in terms of j, some value it has. So let me assign a new index to q also, which is m. So that, and we can further actually use shorthand notation to for this particular state, which is jm, which is understood that it is actually j into j plus 1 comma m. So under this new notation of this state, what is the action of j square on jm? We remember the action was in terms of pq, p h cross square. Now p is in terms of j. Right, what is p? P is j into j plus 1. So the action will be j into j plus 1 h cross square j comma m. The action of j square on pq was p h cross square. Now p is j into j plus 1. So this. Similarly, the action of jz on j comma m was on pq it was q h cross. Now it will be q is replaced by m, so that will be m h cross j m. Okay, so we will use this notation hereafter, which is more familiar from the other branches of physics like atomic and nuclear physics also. So anyway, so we'll use this notation after this. Now our one task is still left, that was what is the action of j plus on pq that we had written in terms of pq was c plus on pq plus 1 something. In new notation, we would like to know what is the action of j plus on jm. It will be, let's say, something of c plus time. Let me replace c plus by k plus, although it does not matter, it will remain c plus because it's just a constant. But let me replace by k plus some constant and jm plus 1 now in the new notation. So we would like to know what is this k plus is, and similarly the action of j minus on jm will be k minus and jm minus 1. We will not to know what this k plus and k minus are. So let's try to find. Let's take the Hermitian conjugate of this equation and operate from the left. So what we get is the following: j comma m, j minus j plus jm is equal to, now since this k plus is a constant, it could be complex in nature, so taking this Hermitian conjugate will make it complex conjugate, and the multiplication with itself will give us the modulus k plus square. And since we have taken these states to be orthonormal, so this will be unity. Jm plus 1 comma jm plus 1, this will be unity because these states we have taken to be orthonormal. So in other words, we have k plus modulus square is equal to bra jm, and j minus j plus is, we have just seen, j square minus j z square minus h cross jz j comma m, which means this is equal to j into j plus 1 h cross square minus m square h cross square minus m h cross square, which is equal to k plus modulus is equal to h cross under the root j into j plus 1 minus m plus 1. So that's what we get, the value of k plus. Similarly, if we do the exercise for j minus j acting on jm and writing k minus as coefficient and jm are the constants and k minus is the constant, j minus 1, and then operating the Hermitian conjugate from the left hand side and do the same algebra, and we find that the modulus of k minus would be under root h cross j into j plus 1 minus m minus 1. So now we know the action of j plus and j minus on j comma m precisely. We know these coefficients k plus and k minus. So let me summarize that. We know the action of j plus acting on j m is nothing but this under root h cross under root j into j plus 1 minus m into m plus 1 and state j comma m plus 1. Similarly, the action of j minus acting on j comma m is h cross under the root j into j plus 1 minus m into m minus 1 j m minus 1. Okay, that's what we know now. Okay, so now we know that what is the action of j square on j comma m. We know what is the action of jz on j comma m. We know what is the action of j plus and j minus on j comma m. What is left is that we don't know what is the action of jx and jy on j comma m. So let's find out that. So the action of jx on j comma m can be find out in the following fashion. We know that the jx can be written as in terms of j plus and j minus like this. And since we know the action of j plus and j minus, so we can immediately write down the action of jx on this. With the j plus acting on this will give us k plus times j comma m plus 1. Now, k plus was h cross under the root j into j plus 1 minus m into m plus 1 j m plus 1 plus half j minus acting on this. So this is going to be h cross. And k minus was under root j into j plus 1 minus m into m minus 1 acting in the state j m minus 1. This is j m minus 1, j comma m minus 1. That's what we get as the action of jx on j comma m. Similarly, we can find out action of jy on j comma m, which will be again in terms of j plus and j minus. Jy is 1 over 2 iota j plus minus j minus acting on j comma m, which is 1 over 2 iota. Action of j plus on this is h cross under the root j into j plus 1 minus m into m plus 1 j m plus 1, and action of j minus on this is h cross under the root j into j plus 1 minus m into m minus 1 j m minus 1. So that is the action of jy on this. Okay, so if we wish, we can solve this bracket also, which is the inside under the root, and we solve it like j square plus j minus m square minus m. So this is j square minus m square, so I can write down j minus m, j plus m plus j plus m, and then plus j from here and a minus m from here. So if I take that common, so this will become jm plus 1. J comma m plus 1. Similarly here, if I take h cross and j square plus j and j plus m this side, this time, so j plus m, j minus m plus 1, j m minus 1. So this is the action of jx and jy on the j comma m eigenstate, which is the eigenstate of j square. And we have found out the action of all the operators involved in the algebra, like j plus j minus jx, jy on j comma m. Okay, the next task is we can have a look on the average or the expectation value of jx hat, for example. So from this we see, so by definition expectation value is this thing. Now since we have taken this j comma m eigenstates to be orthonormal, so in terms of j comma m, if I write down this expression, so this denominator here is unity, so this reduces to this. And now we have just seen the action of jx on this leads to the first step jm plus 1 and the second step j comma m minus 1. So this will give me j comma m plus 1 and j comma m minus 1 as cat, while on the left hand side we have j comma m as bra. So we know they are, since they are orthonormal, so this product is going to be 0. Similarly, same story with the jy hat. So its expectation values of jx and jy operator is 0, which is obvious, which should have been the case, because we know that the angular momentum algebra from the vector notation of the angular momentum, that this magnitude of j, the j vector, actually if it is a z-axis, it revolves like this in a conical shape. If it is a z-axis, it's angular momentum vector j, so it revolves in a conical fashion, maintaining this angle with the z-axis constant, and it can precess around the z-axis like this. So when it presses like this, its component on x and y are both positive and negative, and during one complete revolution around this z-axis, so this average value of this component x and y are actually 0. Okay, but if we try to find out the average of or the expectation value of jx square and jy square, that turns out to be non-zero.